Swayam Prabha. Digital India. Educated India.
So going slightly back, when we did the, you said at 200 nanometer, the sigma electrons will get excited.
Correct.
At that time, will the pi electrons just go to pi star or will they get cleaved?
No, pi would go to pi star.
Okay.
Pi would go to pi star. Okay.
But
you will also have the N2 pi star transitions. Okay. But you are supplying that much amount of energy. Certainly, you must expect a bond cleavage. That's why people, they would advise you not to go out in sunlight, exposed, don't get exposed to sunlight and all that. Because the protein, some of the proteins in our body are sensitive, they are very sensitive, they can cleave. So it can rupture the bonds even. Okay. So such a high energy ultraviolet radiations is what you are talking about. Yeah. But certainly 180 nanometers wavelength you are shining it with, you are going to chop the molecule off into pieces. Okay. That's going to happen. Okay. So this is introduction for you as to what we are going to talk about. Nearly 40 minutes done. So let me tell you how this wavelength could be modified, how we can alter this absorption. Okay. Start with a very simple system. We are talking about ethylene. If you look at ethylene, where it absorbs, it's absorbing in the ultraviolet region. As you can see, it has an absorption around 175 nanometers. Sigma bonds do not play a very significant role in terms of altering the absorption. Inductive effects could be used judiciously to alter the wavelength, but that's not going to give you a significant influence in the absorption spectrum. Okay. Through sigma, you can talk about inductive effects. So that's why we are talking about conjugation effects, where pi extension could be leading to shift in the absorption spectrum. What you are seeing is by adding one double bond, you have shifted from 175 to 217 nanometers, and there is a value just close to that, which is epsilon. You know this terminology, which is molar absorption coefficient or molar extinction coefficient. You have not studied about it. Okay. So what it means is the probability for electronic, it gives you information about the probability of electronic transition in a molecule. Okay. Compared to this has a more probability or less probability of electronic transition. When compared to ethylene, butadiene has a greater probability because it has more number of pi electrons. There it was 2, here it is 4. So there are 4 pi electrons, so probability of electron transition is high, and you are able to see the molar extinction coefficient increasing. Okay. So if you move from diene to triene, obviously you must see the wavelength shifting to higher wavelength region, which means low energy region, and you are seeing the absorption maximum now shifting to 258. Roughly about you will see 30 nanometers shift in every cases, and significantly there is molar absorption coefficient increase. So that means probability of electronic transition increases as and when you increase the conjugation or moving towards a lower energy region. Okay. This is a very popular molecule you may be knowing. Beta carotene. It's a colorful pigment in carrots, right? So this is the chemical structure of beta carotene. When we swallow carrots, we should remember that we are swallowing this compound. Okay. So this particular molecule has 11 double bonds in conjugation. So only when you add 11 double bonds in conjugation, you can shift the absorption to the visible region. Okay. So pushing beyond 400 nanometers or 380 nanometers, which you call it as a visible region, up to what? Up to 780 800 nanometers, you would call it as a visible range. And you can also see the molar extinction coefficient increase so drastically because your population of pi electrons now larger. So probability of electronic transition could be high, and that is shown in that is reflected in the molar absorption coefficient. Okay. So not only in the case of alkenes, I talked about a functional group which is aldehyde. If you extend this conjugation with this particular functionality, then also you will be able to shift the absorption maximum to a lower energy. So here what is shown is acetone, simple acetone. This molecule can undergo N to pi star transitions, pi to pi star transitions, right? And what you will see is N to pi star is absorbing in the lower energy region when compared to that of the pi to pi star. Sigma to sigma star is going to be seen in the absorption spectrum at a very low wavelengths, a very high energy region. So usable absorption spectrophotometer cannot give you that information. So N pi star and pi star could be noticed here with a relatively lower, molar extinction coefficient. If you conjugate it with a double bond, you will start to see that influence is greater in the case of pi to pi star. N to pi star shift will be there, but it is very, very minor. The effect is not so significantly shown here. But if I keep adding double bonds to this, you will start to see the N to pi star shift is also happening, but not to an extent that pi star is undergoing a shift. But there is a shift. Yeah. N means the non-bonding electrons on the oxygen. So they would also undergo electronic transitions at a lower energy regime compared to that of the pi star and sigma to sigma star. So these are the transitions that one can look at. So the colorful molecules, yes.
Sir, but why would N to pi star undergo changes? Because we are only adding more pi electrons that can be excited. Why would the N electrons get affected?
But you have electronic promotion from pi to pi star and N to pi star also.
How is the N to pi star lambda affected by adding more conjugation? You said it's in small amounts it will get affected, but why?
It gets affected because pi star is involved, right? Yeah, N to pi star transition is also there, so that is getting altered as well. So it gets stabilized when you add electrons into it. So a contribution from pi to pi star is also there, N to pi star is also there. So pi star orbital is involved, and hence you see energy alterations with respect to N to pi star transitions. So this is a vitamin A retinol. It's present in our eye. It gets oxidized to this retinol. It gets oxidized to retinal, binds with the protein, undergoes isomerization, gives you a signal as to what we are seeing, right? So vision mechanism you can read about, very interesting mechanism. And this molecule is yellow in color. You can see the number of pi bonds there involved. And moment you go to beta carotene, it is double the amount. You are pushing from yellow to orange, of course. And there are small organic molecules which can be colorful. For example, this compound here that you are seeing is 4-nitro-dimethyl aniline. The molecule that you are showing here is 4-nitro. This is number 1 position. Aniline is simple amino substituted benzene. You alkylate it. You have anion dimethyl aniline. So para position you have nitro group. Now when you have a amino group is of what character? It is, amino group is basic, okay, but I want to know in terms of electron donating, electron withdrawing. Amino group is electron donating group or electron withdrawing group? It's an electron donating group. How it donates? It has a lone pair of electrons, so it does what? Yeah, so you will show it in arrows like this, right? You have so how will you show that? You will take these lone pairs, push it into this, right? And then push it into here, and then push it into this. we can write several different resonating structures. This is how you would have studied. So contribution comes from the nitrogen lone pair into the benzene ring. How do you call this effect? As resonance effect or mesomeric effect, right? So you also have a nitro group on the para position. Nitro group is electron withdrawing or donating? It's an electron withdrawing group. So when you have a donor here, electron donor, when you have an acceptor on the other side, there can be communication between them or not? Yes. There can be communication between them. So if I start moving the arrows, I can move till this nitro, correct? I can move this arrow, right? So conjugation could be extended by appropriately placing a donating group and a electron withdrawing group. You can increase the communication between them. Okay. So this acts as an electron donor, this acts as an electron acceptor. This in photochemistry terms we call it as a push-pull effect or donating accepting effect, or you may call it as a charge transfer which is happening intramolecularly. So you call it as intramolecular charge transfer. Okay. So charge transfer could happen from here to here. This molecule is colorful even in ground state because of the inbuilt push-pull effect that this molecule has. Okay. So it need not have 11 double bonds in conjugation in order to achieve orange color. You can think of placing such a donating group and the acceptor group onto a molecule, provided they can talk to each other, then you will be able to get the color. You can generate color for the molecule. Here is another example. This is a very popular dye. The dye's name is Azure A. Same concept. You have a donating unit here. You also have an electron withdrawing group here. So you can push the electrons from all the way, pump it into this electron withdrawing positively charged nitrogen. Right? So this is an extended conjugation that the molecule establishes with itself in the ground state. Okay. So this molecule is colored in its nature, in the native state. Right? So this kind of a push and pull arrangement could help the molecule to absorb more light, which means the probability of electronic transition increases, epsilon value goes up, and because this molecule is natively colored, you will have the absorption seeing in the visible region. So you are pushing it to the low energy regime. That means you would require lower energy for the electronic transition, S0 to S1. Okay. So this is very, very important. How conjugation influences the color. How you can bring in color into a molecule by suitably placing appropriate substituents. We can modify the color to the molecule. Okay. Something I wanted to ask you. Yeah.
So would you mind repeating how conjugation affects lambda max? I didn't really get that.
Say it again.
So would you mind just repeat? So would you mind repeating how conjugation affects lambda max? I didn't really get that part. The case where you showed
the previous slide.
Yeah, the increasing number of double bonds increased it into a in this case.
So in this case, ethylene to butadiene increased by 1 pi system in conjugation. So this increases the lambda max, which means decreases the S0, S1 gap.
So why does that happen?
Why does that happen?
Yeah.
Because it is getting stabilized. So when you have, so you need to look at in terms of molecular orbitals. So the electronic transition would involve a lesser energy for this process and hence absorption. See, for example, you have ethylene, the molecular orbital. So here this is the LUMO. This is the energy level for this, let us say, and this is the molecular orbital, and HOMO. right? So you have 2 electrons here placed at the ground state. Ethylene has 2 pi electrons. We are talking about only pi electrons, and this is the pi molecular orbitals we are discussing, right? So now 2 electrons. For the electronic promotion, it has to go from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. What we are explaining here is like S0 to S1. Again, S0 is the highest occupied molecular orbital, S1 is the lowest unoccupied molecular orbital, and you have to correlate these 2 terms, sync with it, and then say that electronic transition is happening from HOMO to the LUMO. Obviously, if it's filled orbital, from a filled orbital, electronic transitions are expected to happen. Where it can go to a vacant orbital or anti-bonding or sigma star, pi star, whatever, right? So to the corresponding molecular orbitals, it will go. So now, when you add double bonds in conjugation, right? He's getting it. So when you have, so this electronic transition would require, let's say, X energy, X electron volts. When you give in, this is the electronic transition you are going to promote. Now when you conjugate this with butadiene, you will have four atoms are there. So you can generate, here there are 2 atoms in ethylene, you generate 2 sets of molecular orbitals, linear combination of molecular orbitals, theory if you apply, 4 atoms, so you will generate 4 sets of molecular orbitals, and in that HOMO and LUMO will have, HOMO because you are populating with more number of electrons would rise in energy. HOMO for the butadiene will be raised in energy because you are adding in more number of electrons to the highest occupied molecular orbital sets, they get destabilized. So HOMO goes up in energy. What happens to the LUMO? It is vacant, you populated it, and this comes one step down. Little, not to an extent that HOMO is raised, but it is little stabilized. So the energy gap between this Y electron volts, this should be lesser than X. This way you conjugate more and more double bonds, you will start to raise the HOMOs more and more and lower the LUMOs considerably. At the end, when you have 11 double bonds in conjugation, you will have a smaller energy gap, and the energy gap is worth the value of 465 nanometers, which you can translate it into the corresponding electron volts. Okay, so this is a stabilization that the molecule acquires in terms of electronic transitions, or destabilization of a particular highest occupied molecular orbital, which reduces the Eg of HOMO and LUMO. Okay, so this phenomenon is not only for pi systems. We can talk about benzene also. So a simple benzene absorbs, it's a colorless liquid. Has anyone seen benzene? You've seen it in the lab. Picture of what? Okay, I don't understand. So the liquid benzene is liquid, you know, and that is a colorless liquid. And how about naphthalene? Is a solid or liquid? Naphthalene is a solid. The naphthalene balls that we use, similar. So it is a solid compound, and because you are adding one more benzene unit linearly, you are improving the conjugation. You will see the absorption of naphthalene is until 320 nanometers or so, roughly, right? So it is still in the ultraviolet range, correct? Less than 400 nanometers, it has come up to 320 nanometers. I add one more benzene to naphthalene. What you are seeing is this green curve. Look at the green curve. It has absorption till 380 nanometers or so. So you have pushed the absorption again. So again you are decreasing the HOMO and LUMO energy gap, and hence you are pushing the absorption till 380 nanometers. Now one more benzene I am adding. So it is a tetrazene. Tetrazene has an absorption till 480 nanometers. So moment you have 4 benzene rings attached in a linear manner, or place them in linear way to extend the conjugation, you will see the absorption getting into the visible region. That means, can you guess? Anthracene is colorless. Do you agree with me or not? Tetracene is orange colored. It is colorful. So when you start to see a molecule or a compound is colored, that means it has absorption in the visible region. If a compound is colorless, meaning it absorbs in the ultraviolet region. So you may tell me, sir, why to do visible absorption spectroscopy? To decide where to excite the molecule. Right? If the compound is colorless, then I can use ultraviolet radiation. But what is the ultraviolet radiation, ultraviolet wavelength you want to choose? That you need to know. Till how much? For example, you want to excite naphthalene, you cannot excite here. This is still an ultraviolet region. You cannot excite naphthalene because it doesn't absorb in that region. So it absorbs only till 320. So within 320, now you decide where you want to excite the molecule. Right? So this gives you some idea if you record the ultraviolet absorption spectrum beforehand in order to know where this molecule absorbs and where you want to shine the light. Okay? So if I add pentacene, can you guess where would its absorption be? 500? 580 nanometers. Yeah, roughly 100 nanometer shift is what you are seeing. Right? So roughly 100 nanometer shift is what you are seeing. If you are making pentacene, it absorbs till 580 nanometers. The compound has a blue color. Pentacene is blue, right? It is a purple color, sorry. It's kind of a purple color. So you will have it, you will have the compound exhibiting absorption till 580 nanometers. Now keep in mind, moment the energy gap decreases, that means absorption happens at a longer wavelength, the reactivity of the compound also increases drastically. Because you would need only lower energy to excite, and that is the energy gap it has, so anything it can do within this. So there is no nice discriminated energy levels for it to obey certain things, right? So with the smaller energy gap, moment you start from anthracene, anthracene's reactive positions are what? If you do simple bromination onto anthracene, this molecule anthracene, what would you see? Electrophilic bromination onto anthracene. Where would it happen? These are so many positions. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Where do you think it would happen? It would happen at the middle ring of anthracene, because those carbons, this 9 and 10 carbons, more alike behave like a simple olefin. So any type of reactions you do with simple alkenes, addition, bromine addition, right? All that you can do at these two positions. So believe me, anthracene under sunlight is known to undergo photodimerization. Photodimerization means what? One molecule of anthracene has another molecule of anthracene coming on top. There is a bond formation between these two centers of the stack, anthracene stack, right? So the 9, 10 positions of anthracene would form the bond. And hence what will happen? This would require complete aromaticity. This ring will also achieve aromaticity. The ones that are at the top face, the two rings, they will also gain aromaticity, and you will have the dimer that is generated. So you will have a photodimers generated. In light, you will have photoreactions. So tetracene is also known to do that. Tetracene is orange color. If you expose it to room light, because it's visible light, it can absorb, it would undergo immediate photodimerization, disrupt the conjugation. Moment it undergoes photoreaction, you will see the orange colored compound becoming colorless because it has undergone photodimerization. It has broken the extended conjugation. Similarly, pentacene, the central ring of pentacene, because of 5 rings fused together in a linear way, the central benzene ring alone would undergo dimerization, keeping the aromaticity with the remaining 2 rings, which corresponds to that of naphthalene. So you will shift from 580 to all the way to 320. You understand this part or not? Is there anyone not following this? Tetracene. Let me draw it and show you. It's difficult to visualize probably for you. Right? Tetracene. Now when I shine light, what I told you was it would undergo dimerization. So this 4 pi electrons of this molecule, so in that case I must have to so dimerization can happen between this ring and from the same way from the bottom ring, or it could happen between this ring and this ring, right? So if I draw it the same way, let's assume that it goes the same way. You have so this bond now has to undergo a dimerization. You have a color chalk? Yeah. This is now aromatized, and this is fine, yeah. So here we will have something. You will have these 2 arms going up, these 2 arms coming down, because you are converting an sp2 hybridized carbon, 4 carbons of such type, 1, 2, 3, 4. Which was initially sp2, now have become sp3. So this should be like a butterfly, 2 wings up and 2 wings going down. So now what you have done in this process, you have broken the extended conjugation. Now the conjugation is restricted within this ring, right? Where is the conjugation? It is located only in this ring, and conjugation is located within this ring. The conjugation here in this molecule is within the. So if you record an ultraviolet absorption spectrum, UV visible absorption spectrum for this compound, it will no longer be similar to that of tetracene, but it would resemble the absorption spectrum of naphthalene. Because you generated naphthalene here, this is the light absorbing unit in the molecule, which we call it as chromophore. It's a light absorbing unit in the molecule, which is called as a chromophore. So this absorption spectrum is what you would see in the when you record it. Okay. So what it means is this has undergone a photoreaction upon continuous illumination of light. This tetracene would lose its absorption spectrum slowly, and this new profile you would start to generate. So you would see the absorption of tetrazine decreasing with time under continuous irradiation. Ultimately, you will have no absorption in this region, but finally resulting the absorption of naphthalene. Yeah.
Sir, so any compound with a row of benzene rings?
No, not
Can-
necessarily. Not necessarily. Only if we have reactive units, it would undergo reaction. Such as this. Upon annulation, you will have more and more reactivity associated with the central carbons. So, central carbons are tending to undergo such kind of photo reactions. And similarly, wherever there is a reactive functional group in a molecule with a lower energy, if you supply, it would undergo photochemical reaction if it has absorption at a lower energy region. Yeah. Not all the molecules. Okay. For example, porphyrins have extended conjugation. Chlorophylls have extended conjugation. They absorb light. They have molar extinction coefficient huge, but they don't undergo any photochemical reaction to destroy themselves. No. That's one particular example, right? And carotene we said, retinol we said, they do have absorption in yellow and orange regions respectively. But the yellow region compound, because of its polyolefinic nature, would undergo isomerization across the double bonds. You must have studied cis to trans isomerization, right? Cis to trans isomerization can happen only in the presence of light, because it involves a double bond. You need to destroy the pi in order to be able to rotate the sigma bond, right? Then again ring closure, these radicals would collapse, would form the double bond, okay? So otherwise it's not possible. You can't just like that rotate a double bond like you are doing it for the sigma bond, single bond compounds. So ethane undergoes conformational rotations, right? And long chain alkanes, they keep rotating along their carbon-carbon axis, right? Single bond axis. But double bonds, no. Only using light you will be able to rotate this, because you are destroying this pi in the excited state, and then it would collapse to give you both the cis and the trans. Now, how you are going to populate the trans over cis or cis over trans is about the photochemistry, right? So, otherwise, that's only the way by which you can do. So, in the case of retinol, photoisomerization can be possible. In the case of anthracene, we talked about photodimerization possible, right? So, these are photoreactions as a result of decreasing the Eg gap, okay? So, this is one consequence. So, this structure I wanted to show you. So, we are still in introduction only. We have not gone into the. So, you can see various pigments in different molecules where they absorb, and how their absorption can extend up to, how much they can extend up to. You can see the absorption of chlorophyll up to 700 nanometers can go, right? And lycopene in tomatoes, beta carotene in carrots, lutein in corn. All of these are pigments, and they have visible absorption, and hence we are able to see the color of each one of them. Okay, maybe I should stop and leave you for lunch. Some other time, whenever there is a free slot, I would just come in and talk to you more about photochromism. Keep these things in mind. We will apply that to photochromic materials. Then you will be able to correlate how a material could be designed, how it could be taken to its full potential of such applications. Okay. So, shall I stop here? Yeah, I would like to stop. I will leave you, ma'am. So, I stop here now. They can go for lunch. Their usual time is 12:30 or so. Huh? Yeah, so, let them go. And afternoon you have to go for projects, or there is a session today, a lecture session in the afternoon? No. Okay. Okay. So, all the best. We will see again. I will come some other time. Yeah.